All right, in this video, we're going to go through the 2.4 differentiability DeltaMath practice. Okay, so basically this is just me determining whether or not you guys know the difference between horizontal and vertical. And so horizontal and vertical tangent lines are going to be important for you to be able to identify as far as determining whether a graph is differentiable or not. So for example, on this graph, I notice there are a couple of places where I have vertical tangent lines where my graph is indifferentiable. So like at -7, at 4, x equals 4, right? Those are places where your graph has a vertical tangent line, so we would say our graph is not differentiable there. But this one's asking for where your graph has a horizontal tangent line, so where your derivative would be 0, where your slope of your tangent line would be 0. And that happens, so I see one that happens at -5, right? Because if I drew a tangent line here, it'd basically go horizontal. So -5. And then if you hit the comma, it'll give you an option to put in another one. There's a cusp, that doesn't mean anything. And then at 1, it looks like we would draw a tangent line, that would be horizontal. And then there's a vertical, and then here at 6, if I draw a tangent line, that'd be horizontal. And they're going to do a better job of actually identifying those as well, right? So at here, if I drew a tangent line, here, if I drew a tangent line, and here. They drew little blue ones, I think you can barely see them though. So that's what you do for horizontal and vertical ones. So let's do one where it's vertical. So basically now we're just trying to find everywhere that your graph would be not differentiable due to a vertical tangent line. So nope. I'd have a horizontal tangent line here, horizontal tangent line here. I think at -1 I'd have a vertical tangent line, right? If I drew a tangent line here, it'd go completely up and down. 1, 2, and then at 5 there would be a cusp, and that's about it actually. So I think that is it. -1 would be my only answer. Yepers. Cool. So that's how that works. I think the next one, yep, it's just another horizontal one. So you can work through those. Determining differentiability at a graph. So this one, it wants me to determine where the function is continuous but not differentiable. So for example, like I know my function isn't differentiable here because it has a discontinuity, but they want us to find all the places where your function is continuous but not differentiable. So anywhere that we have a vertical tangent line or a cusp or a corner. So if I'm just following my graph, I notice I have a vertical tangent line at -6. And then I keep going. That's a horizontal tangent line. That's fine. Discontinuity, so it doesn't satisfy continuous but non-differentiable. Discontinuity. Cusp. That would be that would be a place where my graph is continuous but not differentiable. So I have a cusp at 0. Horizontal tangent line, vertical tangent line. So I would need one at 5 as well. Ooh. Not differentiable. Oh, they called it a sharp point. Cusp or corner is usually more used. And then not differentiable due to a vertical tangent line, -6 and 5. Okay, let's try another one of those. Use the graphs to show where the function is continuous but not differentiable. So same thing. All right, so go along at a cusp at -7. Throw that there. Horizontal is fine. That would just have a slope of 0. -2 is not fine though because that would have an undefined slope. So that'd be no derivative there, or undefined derivative. Horizontal. This one's not continuous, so it doesn't satisfy continuous but not differentiable. Same thing with 3. And then 6 looks like it has another cusp. Woohoo! All right. Continuity and differentiability. So this is comparing these two. Oh, so for these ones, you're going to have to determine whether the function is differentiable, continuous, both, or neither at the value where the rule for the function changes. So I usually check continuity first because if it's not continuous even like at all, then there's no way it's going to be differentiable. So if I find f of 3, wow, that's a really thick marker. What's happening? Why is it that way? Try that. Okay. F of 3 would be, let's see, negative 10 times 3 minus 1, so negative 31. That's also my right-hand limit. Okay, and then my left-hand limit would be if I plugged 3 into here, so 3 squared is 9. 9 plus 8 is 17. 17 minus 42. I think that's negative 31. Don't judge me, you guys. It's late, and I'm checking this in my calculator. No, it's wrong. Oh, jeez, the marker's big too. Struggling all the ways right now. So if I had 9 minus, oh, but maybe that's because it's not 42. Maybe it's because it's 48. So 17 minus 48 is in fact negative 31. See, I knew it without even knowing it. So continuous, check. Now we have to check if it's differentiable. So we do the same thing, but you do it with its derivative instead. So let's check. Let's write our derivative first. So f of x prime equal 2x minus 16 for values less than 3, and then negative 10 for values greater than or equal to 3. So then if I do f prime of 3, I would get negative 10, and then that's also my right-hand limit. And then if I check my left-hand limit, I would plug in 3 there. 2 times 3 is 6. 6 minus 16, negative 10 as well. So I would say this function is both continuous and differentiable. Woohoo! And then they do the same thing that we did. All right, let's try it with one more of these pieces. So again, this is where I just right off the bat usually start off with continuity, because if your function isn't continuous, there's no way it could be differentiable. So f of 7, which would also be my right-hand limit, would be 3 times 7 minus 1 would be 20. And then my left-hand limit for my function would be, if I plug in 7 up here, it's 49 minus 35 is 15. 15 plus 15 is not 20. Hold on, 49. Oh, it's 14. I got it. It's 15. So I got 29 as my answer for this one. So there is no way this is not continuous, which means it's not differentiable either. So, function is not continuous, and therefore it cannot be differentiable. All right, let's go back and try some differentiability ones. So, systems of equations. Okay. Determine the values of a and b, which would result in a function being differentiable at x equals negative 3. Okay, so two things would be true if your function was differentiable at x equals negative 3. Number one, your function would have to be continuous at x equals negative 3. And number two, it would have to be differentiable, obviously, because you can't be differentiable without also being continuous. So if that was true, then basically what would have to happen is these things would have to equal each other when x equals negative 3 in order for it to be continuous, and then their derivatives would have to equal each other when x equals negative 3 in order for it to be differentiable. So I'm just going to go ahead and set these equations equal to each other. So 2ax plus 1 equals bx squared plus 6x minus 8 when x equals negative 3. And then if it's differentiable, their derivatives would have to equal each other. So we'd get 2a would have to equal 2bx plus 6. Yeah. Also when x equals negative 3. Let's do it. So plug in negative 3, and I would get Negative 6a plus 1 would equal 9b. Let's see, 6 times negative 3 is negative 18 minus 8 more would be negative 26. All right, so that equation would have to be true, and then this one would also have to be true. So 2a would have to equal negative 6b plus 6. Awesome. Okay, and so now what I'm running into, though, is that I noticed that both of these equations still have an a and a b in them. So in order to solve a systems of equations, you have to either use substitution or elimination to solve these. I'm more partial to substitution in this scenario because I know that if I just divide everything by 2 on this side to get a by itself, I'll get negative 3b plus 3, and so then that's really helpful to, or really easy to plug in for a over here, and then solve for your b value. So I'm going to go ahead and do that. So I'll get negative 6 times negative 3b plus 3 plus 1 equals 9b minus 26. So I get 18b minus 18 plus 1 would be minus 17. That's 9b minus 26. Subtract 9b over, add 17 over, I would get 9b equals 9. Oh, negative 9. Negative 26 plus 17 would be negative 9, which means my b value would equal negative 1. And now that I know my b value equals negative 1, I can go ahead and plug that in here. So b equals negative 1. Oops. Then a would equal 6. Let's try it. Boom, look at that. They do it in lots of words too, but basically set them equal to each other. It looks like they did a elimination. You don't have to. You can do substitution like me. That's up to you. That's how you work out those problems. Then I'm just going to show you one more as well because I'm running out of time to record this video. Okay, so this one, it basically is having you answer the questions about your limits of your original function and your derivative functions as you approach negative 1. So for example, we'll do all the original function pieces first. So f of negative 1, if I actually plugged in negative 1 into my equation, I would get negative 1 squared is 1, negative 1 plus 6 would give me 5. That's also my right-hand limit. My left-hand limit would be if I plugged 5 into there. So let's see. Negative 1 into there. So negative 1 plus 2 is 1. Natural log of 1 is 0. 0 plus 5 is 5. Okay, so automatically I know my function is continuous. Now I'm going to go ahead and find my derivative real quick. So that way I can see if my function is differentiable. So f of x equals, bottom one's easy, negative 2x. For x greater than or equal to negative 1. Top one, technically you have to use chain rule. So your outside function is natural log. Your inside function is x plus 2. Derivative of natural log is 1 over x. Derivative of x plus 2 is 1. Boop, boop. Derivative of the outside, keep my inside the same, times the derivative of the inside. So I would get 1 over x plus 2 times 1. So 2. Lovely. And so now it's basically saying we'll do the left and right hand limits here as well. So for my right hand limit here, I would get, if I plug in negative 1, I would get 2. If I do it my left hand limit, I would get negative 1. So my function is continuous but not differentiable. Wait, what did I do wrong? Oh, I'd get 1 on the top. There we go. And that gives you a whole description of that one. Let me know if you have questions.